CPU architectures, x86 and ARM. Before we start, I have to clarify that for demonstrations, I use data from different scientific articles because I don't have an appropriate ARM-based system to test them myself. So let's begin. Because of recent spike in popularity of ARM CPUs, we need to talk about them and x86 architecture we have been using for over 40 years, and why only now have ARM CPUs become somewhat relevant. And this presentation, in this presentation by the name of x86, I mean all 16, 32, and 64-bit CISC CPUs made by Intel, AMD, and other vendors. And by the name ARM, all commercially available RISC CPUs, Apple Silicon and new Qualcomm Snapdragon, etc. Brief history of x86. All the x86 CPUs are derived from one chip, Intel 8086, with 16-bit registers running at stunning 5 MHz. The following generation added lots of features that now we took it for granted, like floating point unit operations. Before, like Pentiums, there was no floating point unit on die. They were separate. Pipelining, CPU cache, dynamic and speculative execution, Pentium Pro, simultaneous multi-threading, Pentium 4, 64-bit processing, Athlon 64, Itanium, Pentium D, multi-core chips, on-die GPUs, and system on the chip. A not so brief history of ARM began at 1970s. Most of the systems that use them, like the Apple II, were using the MOS technology 6502, 8-bit processor unit. In 1985, ARM Ltd created the first sample of ARM1, their first 32-bit CPU. In 1992, in collaboration with Apple Computers, was created ARM 1610 for usage in their products like Apple Newton. In the future, ARM Ltd discontinued its CPUs and started licensing them. So other companies launched their ARM chips before, like Apple M1 laptop chip. Almost all ARM-based SoCs were used in small portable devices or Internet of Things devices like smartphone, watches, etc. But they started appearing in laptops, and there are rumors about the first desktop ARM-based CPUs. While ARM Ltd focused on licensing its architecture, other companies continue creating their RISC-based CPUs. Manufacturers shown in the RISC-based CPU category almost exclusively made CPUs and SoCs for gaming consoles. IBM PowerPC was used in Nintendo GameCube, Wii, Wii U, PlayStation 3, Xbox 360, and others. The MIPS line at one point used in many HGI computers was used in PlayStation, in original PlayStation, PlayStation 2, Nintendo 64, PSP, and residential gateways like Linksys WRT54G. Now we will, the entertaining part, a bit entertaining part, I would say, is over, and we will talk about some technical stuff. There are a lot of, there are a bit of graphs and numbers, so good luck. First, let's clarify the difference between x86 and ARM. They are shown on the slide, so we will move on to detailed statistics. So power efficiency. We all heard that ARM-based systems tend to be more power efficient until they aren't. So in this slide, there are two graphs that show the efficiency of different systems calculating the Eratosthenes prime number sieve algorithm in C with OpenMP library. And as you can see, ARM plus GPU system is superior to all other systems, both in power consumption and time spent. However, I should clarify that all computations were made only on CPUs, and we can only fairly compare data from Dell EPIC, uses AMD EPIC CPU, and ARM plus GPU systems because they are the closest competitors with roughly similar specs. Now we continue. On the other hand, we have new graphs that displays the same metrics, but for another type of computation, large matrix multiplication. And as you can see, now good old x86 Dell EPIC systems are faster and uses less power. Now there's a question why. So the answer is to this is efficiency, but we thought it was a good thing. Apparently not always. For lesser energy consumption, ARM CPUs operate with a focus on register-based processing, limiting direct memory access, while x86 architecture allow more direct interaction with memory, facilitating a death of computational tasks and expenses of higher power consumption at the expenses of higher power consumption. So in the Rattlesfinn's prime number sieve algorithm, CPU doesn't have to operate memory as much as the large matrix multiplication. That's why those two examples are great for understanding the pros and cons of both architecture in practice. Knowing the practical difference, now we will talk about the core reasons why those architectures behave this way. First of all, instruction sets. RISC architecture has simpler instructions that take one CPU cycle, which make them easier to decode and execute quickly. But because of that, RISC CPUs require more instructions to perform more complex tasks. On the other side, CISC architecture has instructions that take more than one CPU cycle, which makes the execution of simpler instruction a lot slower. However, allows to perform multiple sub-instructions simultaneously and a smaller code size. Second, the main idea behind RISC is to simplify hardware by using an instruction set composed of fewer basic steps. So all execution optimizations are carried to the software. The main idea of CISC, on the other hand, is that a single instruction will do all loading, evaluating, and storing operations in one complex instruction, which allows the CPU task scheduler to optimize the execution of code. But that's what makes CISC CPUs harder to design and manufacture. Third is memory management. So RISC CPUs allow only register-to-register arithmetic operations, which means that they have to pull information to register if they need to work with it. This type of memory usage has some advantages, like lower power consumption. However, because of that, RISC CPUs have bigger registers. But CISC architecture allows to freely use registers and memory, which means they can perform operation with data more efficiently. That's why in large matrix multiplication example, Dell EPIC system got better results. Commercial use. The area of application of ARM-based systems is now even wider than x86 because of how easily we can scale them. We can use ARM-based processors everywhere, from wearable devices like watches to data centers. The same can be said about x86 CPUs. Because of their power consumption, they cannot be used in compact devices. Despite the wide usage of ARM CPUs, some areas like data centers and laptops, PCs, are still dominated by x86. In conclusion, both architectures have pros and cons, and are better suited for different applications because of their specifications. I think soon we will see more usage of ARM CPUs in laptops and PCs, and I hope it will cause innovation in both ARM and x86. Thanks for watching.